post it up there, so after class or during class, if you have your laptop, you can go download it. Oh, there we go. Thank you. You have a different hat on. Just want to make sure you're here. Last spring, I made a mistake of starting like 3 minutes early, and Jonathan squared me away on that. So I like to make sure he's here before I start. Come on, laptop. Oh, you're going to love that. I was fussing about this last night, and now it's just happening. So my Windows is locked up, and I have to do a hard reboot. So I am going to alter while my computer is restarting. I'm going to alter the order of the lecture, maximize time, since we're always in a rush. Okay. Do not fret. I will actually publish. I'll scan this in and publish it online. So today, one of the things we're going to talk about is linear versus binary searching. So when you guys were in the C class and you had a data array, did you have to search for some value? Did that happen? I see some yeses. Are there any no's? Anyone not do that? Search for some value in an array. Okay, well that's cool because I have an example for you later. All right, so on Wednesday we're talking about efficiency. And when it comes to searching for data in arrays, there's an efficiency issue with it. Because sometimes it can be, you have a really large array and you have to go through. So on Wednesday we're talking about that 100 by 100 array. You know, if you had to visit every single one of those cells and you're looking for some value, so let's pretend there's just random data in those arrays instead of the ones and the zeros. You know, it can be very intensive to try and find those different values. So what we're going to talk about today, I'm going to show you a code example of the difference between linear and binary searching and prove to you that the binary searching is actually much more efficient. And there's actually, it's based on this logarithm, log 2, okay? And so one of the things that's important about the logarithm log 2 is it's based in binary. So binary is just your zeros and ones, right? It's like on or it's off. So one of the things that's very helpful, and for some reason, I don't know why it's at the end of the semester. I really would have thought they have done this earlier in the semester, but we have this, this data conversion between the different bases. So we know we have decimal. Decimal are our whole numbers that we're all very comfortable with. But then there's binary, the zeros and ones. There's octal, which goes from 0 to 7. And then there's hex, which goes from 0 to 15. And then, 0 to, there's 15 numbers, but it goes from 0 to 9. Then A, B, C, D, E, and F. So how many of you have used hex numbers when you're defining colors in HTML? Have you seen it? All right, so you're familiar with hex, right? All right, so that's not. Well, there's ways to actually convert between the different bases. And this is a very useful skill to have. And I can assure you that all of these different numbering systems are used on a regular basis in computer science. Who's familiar with a Linux or Unix-based operating system? You ever set the permissions? How do you set them? Read, write, execute, RWX, or do you use the 777, 5? Do you use the octal? Okay, so one of the things about setting permissions on a Unix operating system is there's this concept of giving people permission. You can give them read permission, give them write permission, you can give them execute permission, or you can open the whole thing up. And if you do it with the octal settings instead of the read, write, execute, it's actually done in octal. So 7 is you're opening up to the world, you can execute. And then when you do the read, it's the most minimal, and then the write is the second All right, so I want to show you binary. So this is this concept of log base 2, okay? And I will scan this, and I will upload it on web courses. So when you're doing binary, you actually start from the right going to the left. So you start here. It's grouped in positions and groups of 4. And when there isn't all 4 of them, you just assume you put a pad of a 0 in front of it. So we're just going to go with these different positions here. And then when we get to the chart in the actual slides, it will make more sense. Okay, so these are your binary positions. Again, starting from right to left. So we're going to read it Asian style. And this is your log 2. This is your binary. And then this is your n, or your value in base 10. Okay? So this position is worth 1, 2, 4, 8. So this is how binary works. Every position from the right, very right, going to the left, doubles every single time. Okay? So then we get to 16, 32, 64, 128. And you'll see that this actually is very useful information. 256, and then 512. And now I have to turn the page. I apologize because I'm running out of space. So 1024 and 2048, 40. Yeah, right. I actually had to do the math on this last night because there's no way I could do this real time. You'd be laughing at me like, gosh, she stinks at math. And the really fascinating thing about knowing these values is that it makes so many things in computing make sense that before you're just kind of going like, why? Why is it like that? So think about your memory. How much memory do you have on a system, right? Remember when, oh my goodness, what was the statement that Bill Gates made? Who could possibly need more than 64 meg of memory? Was it 16? So when computers first came out, they were like, who would need more than that? I mean, how much do we have now? I mean, you can buy a terabyte hard drive for like less than $100, can't you? I mean, it just blows your mind. So every position as we're going from right to left doubles in size, okay? So that's what I'm showing you here. And then I have a reference to this in the slides, so it will make sense. All right, so now from a log perspective, this is log 0. This is log 1, 2, 3, 4, 5, 6, 7, and it just increases by 1 all the way across. And then you'll see in our example that I have a chart that just references some of these, where I reference log 3, which is equal to 8, and we reference log 10, which is equal to 1024, and we'll reference log 16, which is equal to 65,536, and then there's a log 20 in there, a log 25, and there's actually a log 30, but I ran out of space. Okay, so as you see this, let me get my system back up and running. You'll see that this actually makes all kinds of wonderful sense. All right, so I'm using CodeBlocks version 13.12. That's the most current version. And I owe you the very specific instructions on how to download and install. And I will put that together this weekend for you so that you have that before your first assignment. So I uploaded this either before or after midnight. Oh, it's definitely after midnight. Okay. So today's lecture is lecture 2. Alright, so and I also uploaded, so make sure you always check the code examples folder on web courses as well, because any code that I display in class is published there. And ideally, if it functions on, it works on my machine. If it functions on my machine, you should be able to download it, pull it into your browser, into your IDE, and it should work as well. So if you go to web courses, go to our class, files, the lectures are under lecture, and the code examples are under code example. Okay? So I always try to publish those before class so that you guys have access to it before you even come to class. All right, so today we're going to talk about linear versus binary. The TA list here is totally crazy. I don't know what's going on with the TA assignments. Ideally, we won't have to worry about it until next week. Okay, so linear search. So linear search, ideally, you probably should have done something like this in your Intro to C class. If not, that's fine. I have code in here that shows you how to do it anyway. So the linear search from a pseudocode perspective is you're just going to look up some value in an unsorted array. And so what you do is if you're going to have an array, you're going to create a looping structure because you want to check every single value that's in that array. So you want to loop through it, right? And so you're going to start at the beginning index. Computer science, typically it's 0, right? We're usually going to start at 0. So we want to check every element in our array, so we definitely want to start at 0. And then we want to check until the length of the array. And I have an algorithm in the code that I have provided that shows you how to find the actual length of the array in C. In Java, it's so easy. It's like blah, 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 dot, length, but not in this case. So that's fine. I'll get over it. Give me a couple of weeks, and I'll stop whining that it's not in Java. All right. So then what you're going to do is you have this value you're looking for. So you're going to compare the data that's stored at each element of your array to the value that we're searching for. And then so you keep looping, looping, looping all the way through that array. If you find that search value, you're going to go ahead and return back the fact that you found it. You're like, yay, it's there. Otherwise, you're going to go, I never found it, so it's not there. From a source code perspective, this is what it would look like. So this is a linear search function. So I'm going to have a return type. I need somehow to indicate that my function, what the result of my function was. So I have this function that specifically is just going to search an array. It'll take any array. So you see that I have a return type of int, and my argument list is an array of type integer, and I need another individual int, which represents the length of my array. And then I have another value, int, is the value that I'm searching for. So that's the signature of my function. So of course, our open close curly braces, don't forget we have to do all this good form stuff. The great thing about using IDEs is usually if you put that open curly brace in there, you hit return, it'll automatically populate with the closed curly brace, and then you can go code in between. So I need this value I to initialize so that I have some variable to use as my looping structure. So my int I is going to be my looping, my control variable. So I initialize to 0 because our arrays start at index 0. And then I'm going to loop until I get to I is less than the length of my array. Because remember, if we have 10 elements in our array, the is actually 9, right? We all agree on that? Okay? So that's why we're doing I less than 9. I mean less than 10. So I'm going to say the length of my array is 10, but I only want to go to index 9 because we go 0 to 9 instead of 1 to 10. And then I'm just going to use the postfix incrementer here so that I just increase so I can go through every single element of my array. And what I'm going to do is do an if check here. If my array index at index whatever, I, so the first time through it's 0, second time it's index 1, and as you know, it goes up to the length of the array. Is it equal to the value I'm looking for? So don't forget, when you're doing an equals comparison, it's a double equals, not a single equal. The single equal sign is assignment, okay? So the I equals 0, that's assignment. So when you're comparing the double equals, you're saying, hey, does this equal that? I know it may seem kind of elementary to some of you, but let's just get back into this idea of coding in C, okay? So if I find it, I'm going to return 1 because that indicates true. You know, from a binary perspective, 0 is off or 0 is false, 1 is true or 1 is on, okay? So 1 means that it's true. And then otherwise, if I go through my whole array and I never find that value, I'm going to return 0 because I didn't find it. So this is a basic linear search algorithm. So code analysis. In the code, I have 2 different data arrays. I have one called an unsorted array of data type int, and I am just doing an inline initialization of it with my data variables. So there's different ways you can initialize arrays. If you don't know what your data set is going to be when you start, but you know how long the array is going to be, you would initialize it by putting some value in between the open and closed brackets there. But if you know the data set, you can just initialize it in line like this. So don't forget, those are curly braces, they're not parentheses. So in my unsorted array, the whole idea of a linear search is probably the most optimal solution you can come up with because you can't make any logical conclusions about that data if that data is unsorted. You have no idea where in the array that value may actually live. So you have to check every element in the array to see if your search value is in there. But can we come up with a more efficient solution? And the answer is yes, absolutely. So one of the things you probably should have been tortured with in computer programming, did you have to sort an array? Yes? Who didn't actually have to sort data? Really? Okay. Well, I'll figure out how to incorporate that. You need that experience. So sorting data. And it's a pretty easy concept. And it's not hard. It's just a practical experience where you definitely just need the algorithm on how to do it, and have that information. Okay. So here's the analogy. You know, guess what number I'm thinking of from 1 to 10. What would be your first guess if I said 1 to 10?
5.
How many would say 5 first? You're on to the binary search right there. Why would you say 5? What's the reason behind it?
Right in the middle.
You're right in the middle. So if I say high or low, you've already narrowed it down, right? You've already eliminated more than half of the numbers to choose from, right? So if I say high, then you're going to go, well, somewhere between 1 and 4 then, right? Because I said 5 was high. So now you're down to just 4 numbers to pick from instead of 10. It makes it easier. Or 9. If I say, you know, if I just said 5 and you said 5 and I go no, try again, you're going, well, can you clue me in one way or the other? You know, I mean, it could take forever. So how do we take that concept that you just said, where you start right smack in the middle, let's make it as easy as possible and say high or low. So I can eliminate more than half of my options. And so we can apply this, and it's called a binary search. So the first thing about a binary search is you have to have sorted data, okay? So one of the things I did not include in my source code example was an actual sort algorithm. So I will make sure that we do that, just so we at least have that code. So from a sorted array perspective, we're going to take that concept, that logical concept that you just said, let's start halfway and at least eliminate part of the set of data to pick from. So from a pseudocode perspective, or from writing it in an English perspective, again, I am going to go through that looping structure, and I do want the same looping constraints. I want to be able to check from the beginning of my array, index 0, to the length of my array, so to the end of my array, whatever the length is minus 1. Now, the first thing I'm going to do is find the middle index of that array. I don't care about the data yet. I just care about the indexes. Give me the middle value. So once I calculate that middle value of that array, that's the first place I'm going to check. So just like you guys said, guess my number from 1 to 10. You said 5. We're doing the same thing, but programmatically, okay? So here, we got that middle, we got that 5, and now we're going to check that index 5, and say, hey, are you the number I'm looking for? And if it is too high, the value, you're going to update that to the current index minus 1. Because you know that from my middle index and above, that data value is too high. I don't want, it's not in there. It's in the smaller set down here. So then we check again. Is that search value greater than the data stored at the middle index? So is that value stored at index 5, is it smaller than the data value I'm looking for? If it is, we add 1 to it and say, okay, from middle to the beginning, you guys are all too small. You don't match my value. I'm only going to look at the top half. And then otherwise, if we fail the fact that it's greater than, we fail the fact that it's less than, it must be true that it's equal from a logic perspective. And so we found it right there at the middle. How lucky are we? So if you have this sorted array data right here, so we need that sort algorithm. Make sure we get that. So we're going to take the unsorted array. We're actually going to sort that data and put it in sequential order. It'll make it easier so we can actually use a binary search. Okay? So here, we're going to search for some randomly generated number. I love random number generators. You know that anyone who took me in OO, I always use random number generators as much as possible. They're very useful. So I'm going to generate some random number. Let's say when I was making the code last night, my random number was 42. So it just depends upon the time of your computer at the time of execution, what number you come up with. So mathematically, I'm going to search between my values. My data here sorted is 2 to 100. I'm going to search between 2 to 100 and find out if my number 42 is in there. Now we can look at visually and go, nope, closest number is 41, right? So first, how do we get to the middle? So we're going to take, what is the average value of our data set? Average value of our data set is 51, all right? But what is the middle index? So we have 22 elements in that array. So how are we going to correlate that search value to the data in the elements at each array? Because if you do it mathematically here with the numbers, it doesn't help you programmatically. We need the indexes. How do we do this with the indexes? So when you're working with arrays, again, our first position is 0. And our last position is going to be calculated as this, using the C programming language. This is very specific to C. Different languages have different options. So I'm going to find out the array of my length, the length of my array. So the length of my array is the size of my populated data array, the whole thing, right, divided by just one instance of it. So from a bit perspective, how many bytes does an integer take up? Four. Yeah? No, in bits. I'm sorry, bits. 4 bits. You're not teaching us that? No? Okay, that's fine. Doesn't matter. Anyways, so what happens is every data type in computer science takes up a specified number of bits, or maybe a byte. Okay, so a character is a bit, but when you do a string, you end up with a byte. So with a short is half the size of an int, so it's 2 bits. An int is 4. If you do a long, which is the double, then it's 8. There's a lot of charts online that show you all that. Do you really need to know that? It's helpful. It really is. One of the things I used to do in the military is, and I'll show you how it does apply, knowing your data sizes. Believe it or not, it really does matter. Bear with me. Man, this room is smoking hot. It's overwhelming here. Okay. So one of the things I used to do when I was in the working military modeling and simulation is I had to transfer data packets back and forth between computers. And we spoke this crazy language called PDUs, or packet data units. Okay, so what happens is we had to explicitly put our data in this little packet. So think about it as a data structure. So you have this data structure that represents something, right? So this data structure, what it's representing is in order to jam electronic signals. So you're going to be able to jam those electronic signals so that anyone who has electronic communications going back and forth, you're potentially interrupting them and creating a problem for them. We had to know how long each field was and make sure that our data fit every single one of those fields. So here, we have this header type here. The whole field itself takes up 96 bits, but then it's broken down into very specific 8-bit, 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 another 8-bit, 32, and then 16, and then another 16. And we literally had to parse out and write these data packets bit by bit. So it does matter that you understand bits and bytes and how those different data values, how much space they take up. And the frustrating thing about that is it depends upon the programming language. So that's just one of those things that it really is an experience deal. But I will definitely find a good reference for you for that, because understanding how much memory something takes up is really important. Back in the day, when we didn't have gigs of data available to us, we really did care about how much space we were taking up. We used to have to make some the shortest variable names possible. So if you ever get into a position where you have to rewrite really old code into something more current, you'll see that we have these crazy naming conventions. That's why we use variables I, and variables J, and variables A, B, C, E, X, Y, Z. They make absolutely no sense whatsoever because we really were limited on memory. We only had so much memory. So we were only allowed to take up 8 bits for our variable name. So literally, that's 8 characters, all we're allowed to take up. So back in the day, this was a really big deal. Maybe not so much now, but when it comes to transferring data, it is important to understand the different sizes.
They learn it in the CDA class. Computer logic and organization.
Computer logic and organization.
Yeah.
When is that? Is that before this class or after this class?
I think it's after.
Oh, okay. So I'm preparing you for a class in the future.
And
How awesome am I?
Part of the final project, you have to know how to parse the bits.
Oh my goodness. All right, we're definitely doing an assignment on that. And you'll be like, oh, done. I got that class already. All right, no, just kidding. Anyway, no, let's focus on what we have to focus on in this class. But I do want you to have the reference material because it is important to understand your bits and your bytes and how much space it takes up, and then every language is a little bit different. So anyways, that's our binary search. All right, so our first index in this example here is 0. Our last index is actually 21 because the array has 22 elements in it, so our last index is 21. Therefore, the middle index is 10. What if you did the actual math on that? 21 divided by 2 is what? 10.5. But we're doing integers, integer division. So when we do integer division, anything after the decimal point just goes away, right? Yeah? Okay. So if we apply this logic, apply this analogy using that logic. So we're going to replace the concept of high or low with computer programming logic of greater than or less than. So your greater than sign, your less than sign. Check the value at index n, whatever that number is, and then programmatically determine the middle index value between 0 and 2. And so we are going to check the data stored at that element. And in this example, we start at index 10, and we're looking at the value of 45. We compare it to our random number of 42. 42 is going to be less than 45, so we can automatically ignore everything from index 10 to the end. In this case, index 21. And therefore, we only continue to check from 0 to 9. So programmatically, again, just keep repeating this process until we find the answer. Is our number in this array? So now we're down to 0 to 9. Find the middle. The middle of 0 to 9 is actually 4.5, but we dropped the 0.5 because it's integer math. So we start at position 4, and 42 is actually bigger than the data that's stored at position 4, so it's 21. So now we're just going to eliminate 0 to 4. And then, so that means that we are going to be only continue checking position 3. Sorry. And then here we're only going to position, so now we're down to 4 to 9. What's halfway between 4 to 9 ends up being 7. What's the data at that position? It's 37. And 42 is greater than 37. So now we're down to 7 to 9. And then halfway through is 8. And when we check the data at 8, it's 38. 42 is greater than 38. At this point, we have already exhausted all of our options because our number was not found. So from a code perspective, this is what it looks like. We have our binary search. We return an int, so we're going to return a 0 for false, a 1 for true. We have our signature of our function, have the name of it, bin search. We have our integer array, the length of our array, and the value we're searching for. We start our low at 0 because we always start at index 0. Our high is the length minus 1 because we start at 0. So our array is 22. Our last index is going to be 21. And then I have this counter. I use this counter so I can output some data to the screen. So instead of a for loop, we're going to do a while. So while my low value is less than or equal to my high, I'm going to find the middle value. My middle index is low plus high divided by 2. So you end up with that 21, right, divided by 2, which is then 10. So we end up with 10. What's the data at index 10 of my array? Is my value less than the data stored in that position? If it is, then I'm going to update my high. Otherwise, is my value greater than what's in there? If it is, I'm going to update my low. Otherwise, it must equal, because I'm not greater than, I'm not less than, so it must be equal. Therefore, we just return that 1. Otherwise, we've gone through the whole array, and we end up with a 0 because it didn't find the data. I have a screenshot in here. All right. My phone says it's 10:06. This clock says it's 10:13. What time do you guys think it is? 10:06. Okay. I know. Well, there is not one clock on this campus, I swear, that actually agrees with each other. Okay, as long as you agree it's 10:06 and you're not all going jamming in like 7 minutes. All right. You know, time is of the essence. If you miss half of it here or you want to hear it again, come to the 11:30 session. Come on in, it's fun. Okay? All right, binary search. So binary search logic after each iteration actually updates the variables low and high. And the reason why is trying to bracket in where is my data in this array. You're trying to find that right position there. So what we're doing is we're updating index values for search in the array so that we're essentially every single time, just like back to the example, I'm thinking of a number from 1 to 10. You're going to guess 5 because you cut your options right in half right there. That's what the binary search is doing for you, okay? And then here, in the code example, the linear search literally checks every single element of the array. It's going to do 22 iterations every single time, no matter what. In our binary search, when I ran this last night, so maybe the data is going to be different, so I might get a different random number, so understand that that might happen. But I have the screenshot embedded in the slides on the next slide. In my binary search example, I only checked 5 elements to come up with that same answer. 5 is much more efficient than 22, right? So here's the screenshot. I have a couple of printf statements in there so you can see what's going on as it's running. So up here you can see the tail end of the linear search where it says that I checked 21 values. Was the number in the unsorted array? And the answer was false. And then here I calculated my middle index at 10. Then it's 4. Then it's 7, 8, 9. I only checked 5 values. Find out the same answer. Much more efficient.
Question real quick?
No.
Okay.
That was your question. Go ahead.
If you're only going to, doesn't this assume you're going to be searching this array many times? In other words, if you're only going to search it once, you have to do all that sorting in the beginning. So
you're right.
Okay.
You're right. You're assuming that you're going to continuously be searching data. So think of it from a
So
large.
you just spend a little bit of time sorting it at the beginning.
Yeah.
And then eventually you're going to
Oh
obviously
yeah. Definitely realize the savings.
And then my other last question is, it'll return 0 because eventually the low is higher than the high. Is that what the algorithm was set up as? I'll look at myself. But like, how does it know to finally kick out of that while loop?
So it keeps looping while my low is less than or equal to my high. If we get to the point where the low continuously is less than, but then we get to the point where they're actually equal, and so you're just like, I still didn't find it.
But it's, in the while loop, if it's equal, it's still going.
Yeah.
So I think either the equal sign or is the low eventually go.
You eventually get eventually get the low and the high are not going to be equal anymore because it's going to. One of them is either get added or it's going to get subtracted. Between the logic right here. See, this is what
So eventually they flip.
Yes. You're going to cross that boundary of the middle index. Sooner or later, you're just going to cross over because you're never going to find that data. So why is the binary search more efficient? Binary search is more efficient because you're repeatedly decreasing the number of elements to compare to by half. So when and the great thing about dealing with odd numbers is it's actually you get 1 extra, because your middle index is, a little bit beyond the halfway point there. So you actually get 1 minus the halfway point. So you're even decreasing the size of what you have to check even more so. So here from an algorithm perspective, so during our first loop, we do n divided by 2 elements. So that's where we're dividing the array in half, saying what's my middle index? Let me check. Where is it in there? When you get to the second loop, now you're actually taking that full array. In our example, 22 elements. You're actually dividing it by 4. Next time through, you're dividing by 8. Next time through, you're dividing by 16. What does that look like? That looks like this. Right here. 2, 4, 8, 16, 32. It doubles every single time. Okay? This is your log 2, right here. So what you end up with, this algorithm, was how we get to log 2. After k number of loops, however many times you're going to loop through, you actually end up, you see that it's always getting raised to the second power. Loop 1 raised to the second power is 2. Loop 2 raised to the second power is 4. All right? 3 raised to the second power is 8. All right, this is just basic math, right? You guys get that? So this is what the algorithm ends up looking like. So after k number of loops, we really end up with this n divided by 2k. But we really want some type of calculation where we want it to equal 1. We want that 1 index, that 1 value. We want to know that our data is there or it's not, down to that 1 last step. Okay? So if we do n over 2k, set it equal to 1, do our basic math to get n by itself. Now n equals 2k, and then our k is actually log 2n. Log 2n, again, is this right here. This is log 2. So a log 8, the value of 8 is 3. The value of 1024 is 10. The value of 65, 536, 16. So I have that in the next slide in a chart. So I put this data here for you so you can see the correlation, but then I will also scan in the handwritten document here where you can see how the binary from every position from right to left increases and how we actually got to that log base 2. That makes sense? It's just, we just double. Just think about the 2, we just double from right to left. Okay? So let's look at the code, because everything makes more sense with code. I have 10:13, so we have 7 minutes. So that is plenty of time. Anyone know how to make this bigger? What is it?
You should just be able to press control and scroll in the mouse.
I don't have a mouse. All right, I will definitely figure that out for next class. I'm not familiar with
Try
this.
Control Plus.
Control plus. We have to shift. Not happening. All right.
With your mouse to the borderline of the code window,
Did it do?
actually shift the column on the left full screen.
I didn't do much. Okay. Yes, I know it's kind of small. I apologize. By Wednesday, because we have Monday off, by Wednesday I will figure out how to make this more readable, because I know in my Java classes, people are like, I can't read that. Can you make it bigger? All right. Well, this is online, so if you do have some type of device, yes.
So in why are you checking to see in the while loop if low is going to equal high? Because how would that happen?
Okay, so let me go through the code here, and then we'll get to that one. All right, so here's my data. So I have my int main. So if you remember back in the day how to write C, you got to have a main function, right? All right, so here's my int main. It's all I need in this file. And so here I'm creating, initializing my array of integers. So I have my unsorted data array, and I have my sorted data array. It's the same data, just one sorted, one is not. I have this first calculation here at line, is that 11 or 12? Line 11. It renders so much stranger on here. All right, so I'm going to find out the length of my array. So in order to find out the length of my array, I do a size of my entire array divided by the size of one value of the array. Doesn't matter which index you pick. It could be 0, it could be 21, doesn't matter. Start at 0 because 0 is pretty safe. I just want to know how many elements I have in there. So overall, it takes up so much space, and then I'm going to say, okay, well, how many are there of those guys? And it gives me a length. My length ends up being 22. Then I just have my printf statement here, and then with my sorted array, just to prove that we have the same size array, so that as I'm showing you that my binary search is much more efficient than my linear search, at least we're definitely dealing with the same sizes, okay? Here I'm just using the rand function from our standard lib header file, and I am going to do a modulus 100. So that's going to give me a value of, if I do modulus 100, ignore the +1 right now. When I do a random, a modulus 100, what's my data range?
0 to 99.
Yes. All right. Everything starts at 0. Awesome. But I want to start at 1. One of my values is not, I don't want the value 0 to be an option. So if I want to do 1 to 100, you got to do that +1 on it, right? Okay. So then I'm just going to output whatever my random number is. And then down here, I'm going to do my result. The result unsorted array. So I call my function search. I pass my unsorted array. I pass my length that I've already calculated. And then I also pass as an argument my random number. And then I'm going to output the result. And can anyone tell me what this is right here? Ternary. Thank you. Anyone who's had me OO knows I love ternary operators. Use them as much as possible. They're so efficient. What is a ternary operator shortcut for? What type of conditional? It's very specific. One more step. If else. It's a shortcut for an if else, right? Remember that? So I'm going to evaluate my value result, 1. And if it is true, I'm going to output the word true. If it is false, I'm outputting the word false. Okay, so this is the true result, the if flag. This is the false result, the else flag. So a ternary operator is shortcut for a standard if-else statement. Love them. Absolutely love them. So you'll see I use them a lot. Okay. So and then the second example here, I call my binary search function, passing my sorted data, my array length, and my number. And then, of course, we have our return 0, which ends our program in C. We look at our search function. This is similar to what was in the slides, except I have some cute little print statements in there that delineate the information that's outputted. And then here's my binary search, which has a couple of print statements in there as well. So consolidate it down on the slide so it was actually readable. I took out all the print statements. So let's run this guy. Who's familiar with the shortcut key F9? Fills and compiles, right? Makes your life really easy. F9. Totally avoid having to use the screen or the menuing. So here, okay. So the length of my unsorted array is 22. My sorted array is 22. My random number is 42. And then here you can see it went through every single element, all 22 elements, to find out that that value wasn't even in there. But then here's a binary search because we started at the middle and we did the low and high termination. We split it. We got it down to just 5 checks. So this proves to you that the binary search truly is more efficient than the linear. That is 1020. Yeah. Now
Where do you guys leave? Hey.
Start. Right here.
Yeah. Hey guys. My name's Kyle Urquhart. I am a SART peer tutor for this class. This is my 3rd semester. Peer tutoring CS1. I'm sure you guys probably already met Jonathan, your SI leader. So peer tutoring is not exactly the exact same thing as SI. What happens in peer tutoring is that our sessions tend to be a little bit longer and more like adapted. Not exactly as scripted as SI in my opinion. So if you guys want any more information, I have flyers with me. Schedule for SART tutoring will be posted on Tuesday. They'll be on our website and they'll also be posted on web courses on your class page. And there's typically 2 places that we meet, engineering 1 to 81. And maybe for this semester, maybe in the park, which is by the CFP Arena next to the Jimmy John's.
Yes.
So I'll see you guys then. If you guys have any questions, feel free to ask me.
It does by default.
Oh, I've never had some pilots.